Okay, let's go ahead and get started. Is my voice being amplified? Not really. Is it useful to have it amplified? Kind of, not really. Okay, let's turn that off. Let's try turning the volume down. Is that okay? Okay, now it's working. You just have to turn it off and turn it on again. That's the secret. I guess it is a little useful. Maybe you can hear me a little better if it's amplified. Okay, today I want to continue with our discussion of the formulation of the theory of special relativity in terms of Lorentz transformations. So I remind you that the basic idea of a Lorentz transformation is that if an observer, let us say S, measures the spatial separation and the time separations between a pair of events, let's call them x1, event 1 and event 2, and their spatial separations delta x and their time separation delta t, then another observer, let's call this observer S prime, who is moving with velocity v in the plus x direction with respect to the observer S, will observe that this pair of events have a spatial and time separation delta x prime and delta t prime. And the relationship between delta x prime and delta t prime is the Lorentz transformation. And it states that there is a linear relationship between the time separations and spatial separations in these two frames. And the coefficients in this linear relationship were derived last time based on the postulates of special relativity. And we checked last time that this way of thinking about special relativity as a relationship between the spatial and time separations as measured by different observers reproduces the same basic effects that we described 2 weeks ago, namely time dilation, length contraction, and the relativity of simultaneity. But the advantage of this way of thinking about special relativity is, first of all, that it will allow us to very easily derive all sorts of other more refined relativistic effects, which will be our goal today and for part of next class. But I think even more importantly than that, this formula for the Lorentz transformation that I have written here can in fact really be used to begin to understand what special relativity is telling us about the basic structure of space and time and what sort of geometry we should associate with the structure of space and time. So that is something that will occupy us for most of next week. So first, however, let's gain some practice with these Lorentz transformation formulas, and in doing so derive a few more of the interesting effects in special relativity. So I would like to consider the following problem. So let us consider an object which is moving with velocity v. Let us call it v1 in the x direction, as measured by an observer S prime, and this observer S prime in turn is moving with a relative velocity v2, again in the plus x direction, as measured by a second observer, S. So the idea is that I, for example, could be the observer S, and you could be the observer S prime in some train moving with some velocity v2. And then in that train, you throw a baseball, and you see that baseball as moving with velocity v1. And the question that I would like to ask is, what is the velocity that I observed for the baseball? We know that length and time become altered in special relativity, so velocity, a measure of the length traveled per unit time, should of course change as well. So in order to compute this velocity, so the velocity of the object as measured by me, observer S, well, if I choose two events along the trajectory of this object, then this u should be the distance traveled divided by the amount of time it takes the object to travel that distance, as measured by me, which will be related to the time separation and spatial separations measured by you in your frame S prime by these two Lorentz transformation laws. So the factors of gamma will cancel when I divide that first formula by the second. And so we obtain for the velocity delta x prime plus v delta t prime divided by delta t prime plus v over c squared delta x prime. So I guess I should say v2 here, because I'm using the Lorentz transformation law that relates time separations as measured by me to time separations as measured by you in frame S prime, moving with a relative velocity v2. Now we can write this in a more suggestive form by noticing that the velocity of the object v1 as measured by you is just delta x prime over delta t prime. So I can rewrite this formula by dividing the numerator and the denominator of this formula by t prime, delta t prime, and then the numerator becomes v1 plus v2, and the denominator becomes 1 plus v1 v2 divided by c squared. And this is known as the velocity addition formula. So let me make a few comments about this. So first of all, what I would like to note is that if either v1 or v2 is much, much less than the speed of light, then the denominator in this formula is very close to 1. And so the velocity as I measure it in frame S will be very close to v1 plus v2. And indeed, that is the standard formula for the addition of velocities in Newtonian physics. So we see, as we would expect, that in the limit where the velocities are very small compared to the speed of light, we get the intuitive expected answer, which is v1 plus v2. Okay. The second comment that I would like to make is that this formula is symmetric in the interchange of v1 and v2. So remember that v1 is the velocity of the object as measured by you in frame S prime. v2 is the velocity of you relative to me. But I could always interchange the role of the frame S prime and the object. And that tells me that that formula should be symmetric if I interchanged v1 and v2. And indeed, looking at this formula, you can see that if you switched v1 and v2, you would just get the same answer again. Now let's consider a few special cases of this formula. So let's consider the case where the object whose velocity you're trying to measure is a beam of light. Okay. so that v2 is equal to c. And so you can easily check that if either v1 or v2 is equal to c, let's go ahead and just do that. If v2 is equal to c, you have v1 plus c over 1 plus v1 divided by c. Multiply the numerator and the denominator by c, and you'll see that the numerator and denominator cancel up to a factor of c, so that the velocity is c. What does that mean? That means that if you see something moving at the speed of light, I see it moving at the speed of light also. That's just a statement that light will travel at the same velocity, namely c, in all reference frames. And the final comment that I would like to make is something that will be a bit of a hint towards physics that we're going to be developing more in the next couple of weeks, which is that if the absolute value of v1 is strictly less than c, so that we have an object moving less than the speed of light, then that implies that the absolute value of u, which is v1 plus v2 over 1 plus v1 v2 over c squared, is also less than the speed of light. So what does that mean? That means that if the object, I guess I should say v2. Let's say v2. Although, of course, since the formula is symmetric in v1 and v2, both statements are true. Or wait, no, let's call it v1. I'm forgetting which one I'm calling v1 and v2. So let's call it v1, because v1 was the velocity of the object. So if the velocity of the object is less than c in one reference frame, then it is less than c in all reference frames. Of course, this is very different from Newtonian physics. In Newtonian physics, you could always go to a reference frame that was moving at the speed of light relative to another reference frame, and then the velocity could change by a very large amount and could be larger than the speed of light from the point of view of one observer. Now, to actually prove this is the case, that the speed of light is always going to be less than c, namely the second equation, that the absolute value of u is always less than c, we could go through the proof if you like, but a picture is worth 1,000 words. So let me just sketch for you a graph of what this quantity u, which is v1 plus v2, divided by 1 plus v1 v2 over c squared will look like as a function of v1 for some fixed v2. So as v2 varies from c to minus c, u will vary from c to minus c. As you know, it should, based on this third point that I made above. And if you wanted to, you could go ahead and plot what the function looks like. It'll look something like that. That's not a very illuminating plot. But you could go ahead and graph it if you wanted to. And you could formally prove, if you like, that the absolute value of this guy is always less than the speed of light. Are there any questions on this? I'm going to move on now to consider some slightly more sophisticated examples. And at the end of the class, I'm going to consider a few different examples of the principles of special relativity in action, just so that we all get a feel for how one would go about using some of these more abstract considerations to solve real-life problems. Any questions before I continue? Yes?
I'm slightly confused as to we did delta t equals original t multiplied by alpha previously. And then
Sorry, delta t is...
1 t over 1 minus.
Yes. Yeah.
We did that, and now we're doing t equals alpha with delta t that. So which one is applicable in which case?
So this is the effect of time dilation that you're discussing. We have to be a little careful about when we apply which formula. So time dilation is the statement that, as we made it a little more precisely last class, that two events which take place at the same location in one frame. Well, okay. Let me just go back to this formula for the Lorentz transformation. So you can see from the Lorentz transformation that it's not just that delta t is gamma times delta t prime, but also that there's this correction factor involving delta x prime. And that correction factor is important. So delta t is gamma times delta t prime only when delta x prime is equal to 0. Okay. So if you have two events that happen at the same location in the primed frame, but at different times, then you can see from this equation here that delta t, so if delta x prime is equal to 0, then delta t is not equal to delta t prime. But it's also the case that delta x is not equal to 0. So even though delta x prime is equal to 0, delta x is not 0. I mean, that shouldn't be terribly surprising, even if you just think about it intuitively. Two events that happen at the same location but different times in a frame here where I'm at rest will appear to you, if you're on some train moving at some constant velocity, to take place at different locations. Okay. You could say that, when we talk about time dilation as derived from these formulas, we have to be a little careful. That's what we went through last time. Generally, of course, provided you're careful about what you mean, the time dilation from one frame to another is the same as the time dilation from that second frame back to the first. Okay. This was indeed, the symmetry was one of the principles that we used to derive this Lorentz transformation formula. Remember, we used the fact that, we used this during our derivation. Okay. I'm not sure if I answered your question. I'm not sure if I exactly understood your question, but I did say some words. Okay. Maybe that's helpful. Questions? Yes. Okay. Let me continue. But please always feel free, all of you, to stop and interrupt me and ask questions. Okay. So far, of course, I have considered events which are located only along a line. So that is to say, I've considered only one spatial dimension, x. You may have noticed, however, that we live in three spatial dimensions. So it's going to be important when considering more interesting physical situations to consider not just reference frames that are moving and events that are located all along the x-axis, but events that are located somewhere in the x, y, z coordinate system. So in general, you could ask the question, if I have a frame, which is to say an observer who constructs a coordinate system where I label the points in three-dimensional space by x, y, and z, along with the time coordinate t, and another frame, S prime, where I label with different coordinates, x prime, y prime, z prime, and t prime, such that S prime is moving with velocity v with respect to x, to s. And of course, now that I'm in the three-dimensional world, I need to tell you what direction S prime is moving relative to s. So let's say that it's moving with velocity v, again, in the plus x direction, with respect to s. Then we would like to understand how these different three-dimensional coordinates are related to one another. And in fact, the answer is very simple. They're related in exactly the way that one would expect. In particular, the x and the t coordinates are related by the Lorentz transformation that we have already derived. And the y and the z coordinates just go along for the ride. Sorry, I dropped a prime there. So in the case where we have a relative velocity between the two frames in the x direction, nothing happens in the y and z directions. We actually saw that already in our discussion of length contraction, where we noticed in our very first lecture on special relativity, actually, that lengths are contracted only along the direction of motion, not perpendicular to the direction of motion. In fact, if that's not clear to you, start thinking about how we define lengths and time intervals in terms of light bouncing back and forth between mirrors, and try and prove it to yourselves. Was there a question? I saw a couple of questions. Yeah.
If you're moving also in the y and z
Good.
axis, you just use a different axis?
Yes.
So it's only the x?
Yes. So for example, let's say that I wanted to just do a simple example of a frame S prime that's moving with velocity v in the y direction instead of in the x direction. Well, what would the Lorentz transformation look like there? Well, then x prime would be equal to x, but y would be equal to gamma y prime plus v times t prime. And likewise, t would be equal to gamma t prime plus v y prime over c squared. Now, the hard case would be the case where you're moving in some general vector, where the velocity v is some more general vector. So here's the case where v is equal to, the v vector is v times x hat. So x hat, do you guys use the x hat notation? That's familiar to you? Okay, good. So v, the velocity vector v is in the x hat direction. This is the case. But an interesting exercise for you to do would be to try and derive this formula for a general velocity vector v. In fact, I assigned that as a homework problem in this class last year, and it was an abject failure. I mean, nobody could do it. But it's totally doable. But you have to think, which is dangerous. Yes. Go. Yeah.
If you're moving in all of the three axes, couldn't you just change the axis?
Yes. Yeah. Okay. I mean, the way that you would answer this question, I think in principle should be clear. Okay. Because all you need to do then is just change your coordinate system so that whatever velocity you're moving, you have the relative motion in, is the one that you call the x direction. Okay. What does that mean formally? That means that you have to first do a rotation, do the Lorentz transformation, and then do the rotation back. So the problem when I gave this as a homework problem was not understanding that intuitively. It was actually writing down the answer correctly. It's not that hard. Maybe I'll do it. Maybe I'll try. Maybe I'll assign it as a problem this year. I'll think about it. There's a question here.
Yeah, if you had an arbitrary path with a velocity, you parameterize the path with respect to t or whatever.
Yeah, we'll get there.
Yeah. Is it like around the same though, which is just with the function?
Yeah. So for example, you could let's take the example. Let's say that I'm very old-fashioned. Okay, and I have a record player. Let's say that you're an ant who's sitting on the record player, on the record as it's spinning around my record player. Okay. Then, in fact, you, as that ant, are not in an inertial reference frame because you would experience the centrifugal and centripetal forces. Okay. And so that's not actually one of the cases that I have considered so far in this class. But we will later on consider exactly what happens for such an ant. And in that case, the relationship between the physics as observed by the ant and the physics as observed by me is going to be a little bit more complicated. Okay. But good question. Yes?
Could you, if v was a general vector, could you just write down y equals gamma y prime plus v y component?
It's a little more complicated. Yeah. It's a little more complicated than that, unfortunately. You would be tempted to just replace the right-hand side of all these equations with the, it's close.
Why doesn't that work?
Okay. Figure it out. Okay. Actually, does it work? I mean, you have to change the t thing, but you could just replace that by v dot x. Actually, that might be just fine. And then gamma is replaced by 1 over the square root of the absolute value of v squared. That actually, I think, is the right answer. Okay, it's not so hard. Actually, yeah. So I think that the right answer is just that x is equal to gamma times x prime plus vt. Is that right? Okay. I'm going to erase that. I have to think about it for a second. I think that's right. Maybe I'll assign it as a problem set. You guys are getting me all excited. Okay. Any other questions? Okay. So let's use that now to answer a second question related to the question that I started out this class with. So let's consider an object moving in 2 dimensions, which has a velocity, let's call it u prime, which is some general vector whose components are ux prime and uy prime, as measured by our observer S prime, who is moving with a velocity v in the plus x direction with respect to the observer S. And then the observer S will see this object moving with a velocity u, whose components are easy to calculate. So u sub x will be delta x over delta t, which is delta x prime over delta t prime, which, using this formula up above, you can see is just u sub x prime plus v over 1 plus ux v over c squared. So this is the identical formula that we derived earlier, because we're discussing the velocity in the direction parallel to the direction of velocity of the 2 frames. And Vy, or Uy, is computed similarly by studying delta y over delta t. So that, just plugging in this formula up here, is delta y prime over gamma times delta t prime plus v over c squared delta x prime. Or dividing the numerator and denominator both by delta t prime, that's u sub y prime divided by gamma times 1 plus u sub x prime v over c squared. Now, I should make one comment here, which is that factor of gamma in the denominator is pretty clear where that comes from, because whenever you measure a velocity, you measure velocity as distance traveled per unit time. And that factor gamma is basically a time dilation factor associated with the fact that when you talk about velocity, what you mean by time depends on who is doing the talking. The other part of the denominator, I suppose, is a little bit harder to interpret physically. But it's there, and we've just derived it. And among other things, it means that the relative change in velocity in the y direction actually also depends on how quickly you're moving in the x direction in a more subtle way than one would guess, simply based on the time dilation effect. However, if you set ux prime equals to 0, so that the direction is purely in the direction perpendicular to the motion of the 2 frames, then you will just get that usual gamma factor coming from time dilation. One comment that I would like to make about this formula for ux and uy is that, among other things, the angle of motion relative to the x-axis changes depending on which frame you're in. That's true in Galilean physics. If you think about it, that'll become clear. But it's just as true in special relativity. And indeed, there's a sense in which this leads to all sorts of other interesting relativistic effects that we might want to consider later, such as relativistic beaming and so forth, which is important in particle accelerators, in astrophysics, and in other cases. Any questions? On this next problem set due Wednesday and on the following one, you'll get lots of chance to practice your skills with velocity addition and all of the other interesting relativistic effects. Yes?
So gamma is using a velocity v?
Gamma is using the velocity v. The gamma factor is always using the velocity that relates the two different reference frames. Absolutely. Good question. Was there another question in the back? I thought, so what I would like to continue to do is use this Lorentz transformation to derive other sorts of effects in special relativity. But I thought that before doing so, I would just like to take a few minutes and just give you a few examples of worked problems in special relativity. Because so far, what I've done a lot of is I've done some formal developments and I've told you about the effects, but I haven't really spent a lot of time actually working through examples. And one of the most important things that I would like to emphasize in these examples that I'm going to work through is that typically, in order to understand the correct physics and to get the correct answer, multiple effects must be considered simultaneously. It's usually the case that in order to make sense of a physical situation, a physical process in special relativity, one has to take into account both time dilation and length contraction, possibly the relativity of simultaneity and velocity addition as well. So let me give you an example. This is a sort of fun example. We're going to take a little poll. So let's imagine that I'm making some cookies. Okay. I like this. This one's in one of your textbooks. I like this example. So let's say that I have a factory, okay, and I make lots of cookies. And I do it by having some dough, okay. This is cookie dough that's moving at some velocity v. Okay. And I have an automated machine which punches out cookies. Okay, I don't know, they're shaped like, well, I can't really draw. I would like them to be gingerbread men, but we'll just make them circles because they're easier to draw. Okay. So we have some hole-shaped puncher. Okay. And every once in a while, this thing slams down on the cookie dough and cuts a cookie. So in Newtonian physics, the cookies that will be cut by this puncher are circular. The puncher is an exact circle. So the question that I would like to ask is that if this cookie dough is moving at a speed that is relativistic, what is the shape of the cookie that comes out? Okay. And I'm going to give you two options. Well, first of all, I'm not going to let you say that it's circular. Okay. Because this is special relativity. But there are really two possibilities. So, if you think about this from the point of view of the frame of the puncher, then the dough is going to be length contracted. Okay. And so that means that after the dough slows down, you'll find out that the shape punched by the cookie is actually slightly longer. It's going to be slightly elongated. Okay. So that would be because the dough is contracted. From the point of view of the puncher. Okay. But what about if you think about it from the dough's point of view? From the dough's point of view, this puncher itself is length contracted. And so that means that the cookie should be punched in a shape that where the direction parallel to the motion is contracted. Okay, so let's take a little vote. Who thinks the cookie is going to be stretched in the horizontal direction, so there are two possibilities. A, where the cookies end up stretched in the direction parallel to the motion, and B, where the cookies end up stretched in the direction perpendicular to the motion. Okay, who votes for A? Good. Who votes for B? Who wants to explain why they voted the way that they did? Does that, anyone? Yeah.
I'm just wondering if that's true in moving vertically, is when you see the bottom of the punch behind.
Okay, the punch is always going to be level, but you're thinking along the right lines. Okay, I'll give you a hint. The hint is the first line that I wrote at the top, which is that multiple effects need to be considered. So in order to understand what the punching out of the cookie dough looks like, okay, so at the end of the day, the cookies are going to have a shape. Okay, they're either going to be stretched in one direction or the other. That shape is physics. Okay. And which answer you get for the shape better be the same in no matter which reference frame you use to analyze this problem. Okay. You could analyze it from the dough's point of view. You could analyze it from the puncher's point of view. You better get the same answer. However, just using the effect of length contraction, I seem to have gotten the opposite answer, analyzing the problem in two different ways. And the reason why one of these is wrong is that it fails to account for one of the other important effects in special relativity. Does anyone want to guess what that effect is? What? Simultaneity. Because when you say, so let's imagine from the point of view of the puncher. Okay. From the point of view of the puncher, the two endpoints, let's say that we have the left-hand side of the puncher and the right-hand side of the puncher, they're going to hit the dough simultaneously. And so the answer that you get in the frame of the puncher is going to be the right one. If you try and analyze it from the dough's point of view, you better take into account the fact that the events where the left and the right-hand side of the puncher hit the cookie dough don't happen simultaneously. One of them happens before the other. So the answer is A. And the reason is that the punching is simultaneous in the frame of the puncher, but it is not simultaneous in the frame of the dough. So if you want to analyze this problem from the point of view of the cookie dough's frame, then indeed the puncher is length contracted. Okay. But the two ends of the puncher don't hit it at the same time. So you were basically right when you said that the puncher looks like it's coming in at an angle. So this is a great example because I didn't have to write down any equations or anything like that. But you can easily see that if you don't take into account all of the effects of special relativity at the same time, then you can very easily confuse yourself. Okay. At the end of the day, the physics that you get has to be independent of who is describing that physics. The outcome of any physical experiment, such as the eating of a cookie, has to be independent of whichever coordinate system you use to describe those events. This is one of the basic principles in physics, that the physics of a situation, at the end of the day, has to be independent of whatever coordinates you use to try and describe that setup. The coordinates associated to S prime, or whoever. Question?
But in the twin paradox, that acceleration...
The twin paradox is one of my next examples. Let's talk about that, okay, when the time comes.
The incline of the puncher?
What's that?
If you're talking about the incline of the puncher, then
Well,
the end on the left side is lower than the end on the right side.
Yeah. Yeah. Exactly. So how would it be? It would be that the left side will hit the dough first before the right side. And remember that the relativity of simultaneity, which event happens? So the two events, the landing of the left and right side of the puncher, were simultaneous in the frame of the puncher. That's like the definition of the puncher, I suppose. But which one happens first depends on two things. It depends on which one happens first from another frame depends on the direction of the velocity. Okay. So go through the Lorentz transformations and check that indeed the left-hand side of the puncher hits before the right-hand side of the puncher. Good. Okay. Let me do another example. So let's say, I'm not going to go through the whole details of this example. I'll just sketch out how the problem might work. This is similar to the sort of problem that you might be assigned on a problem set. So let's consider two passing trains, each of which has a length when the train is at rest of L. So here's train A. It's moving with some velocity v1 from my point of view, so here's me, an accurate artistic representation, at rest with respect to the train A. And then there's a second train, B, moving at some velocity v2 that is less than v1 from my point of view on the ground. Okay, let's call me C. I'm here on the ground. So let's ask how long it would take train A to pass train B from the point of view of the observer C. Okay. That's a relatively easy question to answer. So I should say, how long does it take A to pass B? I mean, for the front of train A, for the back of train A to pass, the time it takes from when the front of train A is next to the back of train B to when the back of train A is next to the front of train B. So V2 minus V1 is the relative velocity of A with respect to B as measured by C. So that's the relative velocity of the two trains. And then we should ask how far they have to travel. So they must travel a distance, well, the length of train A plus the length of train B, for train A to go from completely behind B to completely in front of B. And so that distance will be L times the gamma factor associated to V1, that's the length of train A, plus L times the gamma factor associated to train 2. So I'll just call those gamma 1 and gamma 2. That's gamma for V1 and gamma for V2. So the total time it takes for the trains to pass one another, from my point of view, is the ratio of these two, gamma 1 plus gamma 2 over V2 minus V1. Okay, that was easy enough. Let's now ask the slightly more interesting question, or slightly different question, which is how long does this take from A's point of view? And I don't actually really feel like I need to work through this out in terms of all of the equations. But what I want to point out is that there are really two ways of doing the calculation. And that depending on how you choose to do the calculation, you might use different effects in special relativity to get the answer. So for example, you could take the answer for TC and then use time dilation of TC to put it in A's frame, and that would give you the answer. Or I could do a different calculation. I could determine the velocity of B with respect to A using the velocity addition formula. And then determine the length of B with respect to A using length contraction. And then I could take their ratio in order to determine the amount of time it would take from A's point of view. So you can see there are two different ways of doing the calculation. One uses time dilation, one uses velocity addition plus length contraction. And, of course, these two different ways of doing the calculation should give you the same answer. So, depending on how you choose to view a particular series of events, one might either view this as an effect of time dilation or as an effect of length contraction along with velocity addition. So, it really makes no sense to talk about the effect of time dilation as opposed to the effect of velocity addition or length contraction. They're really all interrelated. And if you want to get the correct physics answer, you need to take them all into account at the same time. And if you don't do that, you're destined to failure. You're going to get in trouble, for example, if you try and figure out the shape of a cookie without remembering both time dilation, length contraction, and the relativity of simultaneity. So let me end up with a final example, which is that of the twin paradox. So let's imagine, so this is something that you all probably have heard of before. So let's imagine that I have two twins here on Earth. I'll call them A and B. Okay. I'm not very good at coming up with baby names. Just ask my wife. Twin A will stay here on Earth. And twin B is going to go off to Alpha Centauri and then come back again. So twin B will move with some velocity v towards Alpha Centauri, and then with the same velocity b back to Earth. And then, at the end of the day, A and B are both going to be back on Earth. And we should ask, which one is younger than the other? And there are two possible answers. So we could say that A is younger than B, since, from B's point of view, A is moving, and hence time dilated. Or you could say that B is younger than A, since for the same reasons, except with A replaced by B, since B is moving with respect to A. And the twin paradox is not the paradox that one twin is younger than the other. It's the paradox that apparently you can derive either result by depending on which reference frame you choose to use to do the calculation. However, one of these results is wrong and one of these results is right. Which twin is older and which twin is younger is a statement about physics. The answer that you get should be the same independent of who is doing the measuring. So what's the answer? Let's take a vote. How many people think that A is younger? How many people think that B is younger? Okay. It's because you've seen Star Trek or whatever, wherever this is referred to in the popular media. So the answer, of course, as most of you got correct, is that B is younger. Just as science fiction taught us. Why? Who wants to volunteer? I actually told you the answer already, but go ahead. Exactly. The point is that A's frame is an inertial frame, whereas B's is not. In particular, when B arrives at Alpha Centauri, he has to accelerate. And so because of that, he'll experience these non-inertial forces, because he's in an accelerating rocket ship. And so when B is turning around at this point in Alpha Centauri, at the end of his trip, or halfway through his trip, the rules of special relativity, as we have worked them out, cease to apply. So in particular, if you imagine what happens is that as B is moving at constant velocity towards Alpha Centauri, from his point of view, his twin A is indeed aging more slowly. And indeed, when twin B is on his way back from Alpha Centauri, his twin A will appear to be aging more slowly. However, at that point where he's turning around, A is going to be aging very, very, very rapidly to make up the difference. Yes?
In David's Martin's book, it says that you can also include this in the result without the acceleration. Without taking into account the acceleration.
Well,
how would you...
I mean, one has to, you can always put the, I don't know exactly what you mean by that. Okay.
Even if you don't take into account the acceleration effect?
Yeah. No, I mean, when I say, so you could take B to be moving at constant velocity from here to Alpha Centauri and at constant velocity back again. But what will happen is that the spaceship will be, has to stop and turn around. Okay. So there is acceleration taking place. Yes, even if he does a circle and doesn't stop, there's still acceleration that's taking place. Because at the end of the day, B has to stop on Earth. Yeah. Right, and that's an acceleration. I mean, there might be a semantics issue. I don't know in exactly what sense Morin is using the word acceleration here. We will, unfortunately, I'm also a little out of time, but we will consider in more detail exactly how one would take into account this effect. Okay. I suspect it's more semantics than anything else. Okay. Maybe show me in his book.